So for question 2 for part 2 of the paper, the second half of the paper, you have to simply describe the hydrogen emission spectrum. A lot of you try to explain what was going on in it, you simply have to describe it. Let me remind you what it looks like. You've got a spectrum which you've got total of something like 4 lines, I think it's 4 lines on it, and you do not have to remember it in detail, but you do have to remember a few points. So you have to remember that it's a series of lines, and that will do, or you could say there are specific frequencies and they converge. In other words, they get closer together at higher frequencies. So if it says describe something, that's the key message here, is you have to describe it. Okay? Turn this light off. Okay, hopefully you can still see okay. Just going back to this hydrogen emission spectrum, which you were taught back in the atomic structure topic, this series of lines on here, these are about 400 nanometers, and this is about 700 nanometers down this end. So this is high energy, this is low energy, so hopefully you can remember all that stuff. It's worth looking back. If you've forgotten how the hydrogen emission spectrum comes about, or you've forgotten what it looks like, it's worth having a look at, and these obviously have got different colours associated with them. Okay, I'll stop there. How is the spectrum related to the levels in the hydrogen atom? Well, you, back in that atomic structure test you did way back last year sometime, you'd have had to draw an explanation for it, which looks something like this. You have a spectrum here, you have the energy levels for hydrogen drawn and numbered, n equals 1, so the principal quantum numbers labelled, n equals 2, 3, 4, and so on up to infinity. And what happens when you get a hydrogen emission spectrum is the electron, because hydrogen's only got 1 electron, starts off in the first shell, or the energy level with the lowest quantum number. It's given energy and it jumps up into one of the higher energy levels, and then when it drops back down again it releases energy, and it's the releasing of that energy which releases light. And all you have to say for the mark was it's a transition of an electron from a higher energy level to a lower energy level. Or you could have been a bit smarter about it and really clever about it and said, okay, for light to be given off, you might remember this is the transitions from the upper energy levels to the second energy level. Okay, so you have to say in words the transition of electrons from higher energy levels to lower energy levels, but that explains it. When I scan this, I'll put the full answer in there. Okay, the next question I'm really not going to spend any time on. I think just about everybody, if not everybody, got the answer of 24.33. If you want any help with working that out, give me a shout. All you have to do though is multiply the mass by the abundance, add it to the mass times the abundance, add it to the mass over the times the abundance, divided by the sum of the relative abundances. Because these are percentages, they should work out to be 100, although I haven't checked. Okay, nice and easy, most people got that right. The next question though was something more of a battle. Just looking at my workings out here, where is it? Here we go. So I'm going to walk you through this next question where you have to work out the empirical formula of menthol. It's not a compound you've come across necessarily, you might have heard of it, but you're not expected to have known what the structure was. You're supposed to work it out to a certain extent, or at least to work out the formula of it from this. So just as a little kind of start you off, so you're told it's got made of carbon, hydrogen and oxygen, so CX, HY, Z, start again, CX, HY, O, Z. Obviously that's reacted with a certain amount of oxygen, we don't know how much, to give you carbon dioxide and water, and we don't know how much carbon there is in here yet, or hydrogen or oxygen. We've got to work that out piece by piece, and let's be honest, it's not that easy. But as I always try to encourage you to do, just write down what you know and see how far you can get. You might pick up some marks. Okay, So menthol, you're told you've got 0.1595 grams. We don't know how much oxygen there is, doesn't really matter. We're told we've got 0.4490 grams of carbon dioxide produced, 4490, and we're told we've got 0.1840 grams of water produced. Okay, but we need to know, if we don't know what we're doing, we've got to try and work out the number of moles. We don't know what the MR of this stuff is yet, so we can't work out the moles of that. We do know the MR of carbon dioxide is 44, and the MR of water is 18. So we can work out the moles of carbon dioxide and the moles of water really easily. And the moles of carbon dioxide is 0.0102, and this is also 0.0102. Okay, so we're working out the number of moles of those things. But for an empirical formula, remember we have to work out the number of moles of carbon and hydrogen and oxygen. And then we go through a process which I've taught you. Now the number of moles of carbon is equal to the number of moles of carbon dioxide, but the number of moles of hydrogen is twice the number of moles of water, because there's 2 hydrogen atoms for every molecule of water, or 2 moles of hydrogen for every mole of water. So the moles of hydrogen is twice that. Okay. So let's put that down. So moles N of carbon is equal to 0.0102, wasn't it? Yep. And the number of moles of hydrogen is equal to twice that, which is 0.020. Whoops, I've written that wrong. 0.0204. Sorry, I'm looking ahead. Right, but that, how many grams or moles of oxygens are in menthol? We don't know yet, but we know the mass of menthol, and we know how much of that mass. We can work out how much of that mass is carbon by multiplying this by 12, which is equal to 0.1225 grams. And we can work out the mass of hydrogen in menthol by multiplying the number of moles of hydrogen by 1. Well, 1 point whatever it is for hydrogen, that comes out to 0.0206 grams. Okay, so therefore the mass of oxygen in menthol is equal to this mass, take away this mass, take away this mass, which comes to a little pause here because I lost my little crib sheet. Here we go. The mass of oxygen comes to 0.0164 grams. Okay, so the approach to doing empirical formula is the same as it has been forever. So we've got the atoms involved to carbon, hydrogen, and oxygen. Not much room to do this question in this little space, but you do get access to scrap paper, I think. So you can just plug the moles straight in if you want to, but we can go through the whole process, I suppose. So 0.1225 grams, 0.0206 grams for hydrogen, 0.0164 grams of oxygen. The AR for each of those elements is 12, 1 and a bit, and 16. And you can work out, so step C is work out the number of moles. I've already done that before, which is 0.0102, 0.0204, 0.01025, and that turns out to be a 10 to 20 to 1 ratio. So the empirical formula, I'm going to squeeze into this tiny box here, which is C10H20O. Okay. The next question is a fairly routine PV and RT question the way that it's set out in the mark scheme is not exactly the approach I would take, and that does all the rearranging to start with, and it's plugging in numbers which work, but I'm going to go about it the way that I've taught you, which is to start off by writing PV equals nRT, and then rearranging to figure out the thing we need to find out. So we know the pressure, we know the volume, we obviously know R, because it's the gas constant, and we know the temperature, 150 degrees C, we've got to convert to Kelvin, and we need to work out the number of moles. Okay, if you're not sure what to do, work out the number of moles, and then we have to work out, so let's rearrange that now, N equals PV over RT, and the MR, of course, is equal to whatever the mass is, which is in the question, which we know, divided by the number of moles, which we're going to work out from PV and RT. Okay, this should be dead straightforward, absolutely routine question, comes up all the time, couple of marks, easy peasy. But what we've got to do, if we do it the way that I taught you to do these, you've got to plug in the numbers using the appropriate units, which is not how it's set out in the mark scheme. So I would convert this to pascals first, which is what I taught you. So pressure's got to be in pascals, volume in meters cubed, so we've got to convert to meters cubed, R is 8.31, and temperature's got to convert into Kelvin. So pressure is 100,200. The volume in meters cubed is 3.37 times 10 to the minus 5. R is 8.31, and T in Kelvin is 423, and that comes to 9.61 times 10 to the minus 4 moles. So MR is equal to the mass, 0.150 given in the question, divided by 9.61 times 10 to the minus 4 equals 156. Whoops, 156 grams per mole. Should be routine, that, absolute routine. And because, so the next question is to determine the molecular formula of menthol. We know the empirical formula is C10H20O. So you find out the MR of that, so 12 times 10, 1 times 20 and 16, that comes to 156. So the formula, the molecular formula must also be C10H20O. Okay? So you couldn't really do this question without being able to do this in this one. Right, and then the next one, so just put my calculator there. This is again a fairly routine rate equation question when you're given initial rates information. So this is when you do a series of experiments, changing usually one concentration at a time, finding out the rate and finding out what effect changing the concentration has on the rate with respect to each of the reactants. So in the first experiment they've got concentration of both the reactants is the same. The second reaction they've doubled the concentration of the chlorine. The third reaction they've kept the concentration of chlorine the same as in experiment 2 but doubled the concentration of nitrogen oxide. Okay, so the way that I go about this is I look for the change. So that stayed the same from there to there, so I just put times 1. Yeah, there to there it's doubled, and the rate there has doubled. So that's telling you the reaction is first order with respect to chlorine, so 1, or first order. Tick. Second one is as you go from here to here, concentration stayed the same, so write that, and then the concentration here is doubled, but the rate is times by 4. You might need to get a calculator out. Don't be afraid to get a calculator out and do 3.16 divided by 7.9 times 10 to the minus 1 and find out that's a multiplication of 4. So doubling the concentration gives a 4 times rate increase, which is 2 squared, so that would be a second order reaction. If they'd have tripled the concentration, you'd get a 9-fold increase in rate because it's a second order with respect to nitrogen oxide. So the rate expression, rate is equal to K NO squared Cl2. Okay. whatever you got for these, if they matched this, then you got the mark. Okay. For the last one, I've already done the sums. Right, this is pretty common use then of the rate equation that you've used. So here's the rate. I wrote the rate equation out again, but then you rearrange to make the rate constant the subject of the equation. So the rate is equal to, K is equal to the rate divided by the concentrations raised to their appropriate powers, and bring it up there. All you've then got to do is drag the numbers from any of these rows. It could be the first row, the second row, or the third row. You get the same answer each time. I used data from the first row where the rate was 3.95 times 10 to the minus 1, and the concentrations were both 1.3 times 10 to the minus 1. So, whoops, done that wrong. So it should be cubed. So it's 1.3 times 10 to the minus 1 squared times 1.3 times 10 to the minus 1 is equal to 180. And you might have put the units there, you didn't need to for the marks. I've left it like that. And that, I think, is it for question 2.